In this final video lecture for this week, we're going to look through the consistent structure required when putting together Pytorch networks. We will also look at the structure of training and test loops. In particular, I will start by walking you through an example for a simple linear regression, and then in Thursday's tutorial we will ask you to work through the same steps, but instead for a multi-layer perceptron for MNIST classification. To start with, let's go through the checks required to confirm whether your code is using GPU or CPU. These lines of code just tell your scripts or notebooks to use a GPU if one is available and otherwise use CPU. For this week, CPU will be more than sufficient, but in later weeks when your images get larger, you're going to want to use a GPU. Don't forget that if you want Colab GPU support, you must change the notebook runtime as shown in the introduction video. Now let's review the high-level steps of training networks in Pytorch as introduced in the previous lecture. What we first need to do is create a bespoke network class which inherits from the Pytorch nn.module base class. This will define our architecture. You will then need to create an instance of that class, a network object, which you can then forward and back propagate through. Next, you are going to need to choose a loss function and optimizer from one available from Pytorch. Then you can set up your training loop where you will repeatedly perform forward and backward propagation by enumerating over all training examples in batches, typically using a data loader. A typical training loop then involves a forward pass, which corresponds to just 2 lines of code. Then back propagation is a bit more involved in that you must remember to clear gradients at the beginning of each training iteration, otherwise it's handled in the background through the loss.backward function. Finally, at the end of the training loop, you just need to call the optimizer to update the weights, and that's it. The whole thing reduces to a very few lines of code with Pytorch handling all the complicated stuff in the background. Let's start by looking at how to define a network class. This is probably the most complicated bit, but after a few goes you should hopefully get used to it. Essentially what you need to do is create a class. You can call it whatever you like, but it must inherit from nn.module, which you can see it does by specifying nn.module here. This will allow it to access all of the nn.module base class functions. Of those, you just need to overload the constructor init and the forward function. When writing your init function, you must start by specifying this superline, where the first argument needs to be the network name, specified here. And the second argument will always be the self keyword, i.e. referencing the instance of the class that gets created. My high-level advice to you at this point is that what you need to be doing is copying the basic class structure from an existing network and then replacing all the lines of code below the superline of the constructor and in the body of the forward function as well as its return statement. Optionally, you may also want to replace the name of the network with something more descriptive here and here. In doing so, for the constructor, what you need to do is define your layers, or all the operations with trainable parameters. So here we have convolutional layers, we have batch norms, and we have linear layers. These have their arguments hard-coded in. So the number of input channels or features is given as 3. The output dimension of the first convolutional layer is 64. The output dimension of the second convolutional layer is 128. You can either define the arguments in this way, which then makes your network parameters non-flexible, or you can pass them as arguments to your constructor. Then, moving on to the forward function, this is where you piece everything together in order. In this case, it takes an input, it applies a convolution, then a batch norm, then a ReLU activation, and this process repeats for 2 layers. You may notice that the ReLU is applied using its nn.functional form, indicated by f.ReLU, and is applied directly in the forward function. This is because it has no trainable weights. Same for the softmax at the end. Note, you don't need to define backpropagation at all. This is handled automatically by the autograd class through application of the backwards function on the loss. We will look at this in a minute. Then, once you've defined your network, you can create an instance of it by just calling it in the following way, using the class name, open and close brackets. Next, loss functions and optimizers. So Pytorch provides efficient implementations of a large number of loss functions and optimizers, keeping very up to date with research. So all you really need to do is search through the available options in Pytorch and choose one. Some popular examples of loss functions that we've seen already are cross-entropy, where this is specifically multi-class cross-entropy, and there's a separate function for binary cross-entropy. Also, we have here mean square error loss, which is an option for regression. During the training process, when you subsequently need to estimate the loss, you just need to call the function using the name that you gave it when you created it. For example, loss_CE, here for the cross-entropy loss. It takes as argument the prediction output from the forward pass and the ground truth labels, here called target. For optimizers, you again have many choices, but we won't go into any details on this today as we'll cover it in more detail next week. Let's just use stochastic gradient descent for all our networks this week and keep the parameters fixed. So this is defined in the following way. You just first pass your network parameters, where net here is the name of whatever you called your network, as you can see here. Then LR stands for learning rate, and this momentum parameter as well we'll talk about next week. Before we go on to training, I just want to directly address a point of ambiguity. I've told you as a rule of thumb, apply activations in the forward layer using the functional forms. So here, f.relu, f.log softmax. Actually, you can put them either in the constructor or in the forward function, where in the constructor you need to use the torch.nn versions. I would stick with the rule that I've given you, but be aware that you may see differences in other people's code. Also, and we will cover this in more detail next week, there is a module called nn.sequential which allows for speeding up during training by grouping operations of the graph together in blocks. You need to define these blocks in the constructor, and so when you do, you need to define activations using the torch.nn form. Right, so that's the difficult bit over. So now we can look at performing forwards and backwards passes. Some notes. First, when defining your training loop, you never explicitly call the forward function, rather nn.module handles this behind the scenes. For an explanation, you can read this source. That doesn't mean to say that you don't code anything, but rather the forward pass looks something like this. You call your network, pass the inputs, and it outputs a prediction. You'll need to then calculate the loss after this step. For the backwards pass, you then need to call loss.backward and apply the optimizer using the step function. In addition, it's really important to remember to clear the gradients before every training iteration, and we'll look at how to do this in a second. This avoids mixing up gradients between mini batches. Note the reason that it doesn't do it by default is that it can be a useful feature, for example when training networks which need to accumulate gradients such as recurrent networks. So let's now go through the simple example from section 6 of the notebook. In the first instance, we're just going to look at linear regression, which equates to implementation of a single linear layer. Here, we're going to model data with just one feature. So the input has dimensions 1, and the output has dimensions 1. So all we need is to define this one layer, this one operation, and then just call it in the forward function. It's linear regression, so no activation is required. Once done, we need to create an instance of it, which we're going to call net. For reference, we can print out the network, and it will report the layers and their operations. The next thing we need to do is create a loss function and an optimizer object. We will again use SGD for optimization, and because it's regression, we're going to use the MSE loss. Now we can focus on the training. So in the simple case, we don't need a data loader. Our data set is tiny, so we can just estimate our loss over all examples each time. Therefore, we just loop over training epochs, where epochs should always define time taken to loop over the whole training set. Looking at more detail at the loop and remembering this basic structure as it will always remain basically the same, we first need to clear the gradient stored by the optimizer in the following way, calling 0 grad. We then perform a forward pass, just passing all our data to our network. The forward pass is then handled by the nn.module in the background. This gives us a prediction for this iteration, which we can use to calculate the loss. We then run loss.backwards, where the autograd class will plug in the current variable values to return the gradient using the analytic derivatives it stored as it created its computation graph. The final thing we need to do is step in the direction of decreasing gradient using an update rule which is controlled by the optimizer. The code below then just plots the predictions for each training iteration. I suggest you try this in your notebook. Then, in the tutorial on Thursday, we will ask you to extend this approach to instead code up a fully connected MLP network architecture trained on MNIST. So your training loops should stay the same, bar the fact that you will need to use the Pytorch MNIST dataset and data loader and won't want the same plotting functions. We will, however, need to create a new network class which encodes a specific fully connected network architecture. To do this, you're going to have to go back to lecture 4 to reference the diagram of network shape. While you do not absolutely have to know how to code this from scratch, you do need a firm grasp of how the network structure impacts the shape of your weights matrices for each layer. Remember, the number of neurons from your previous layer is the number of input features, and the number of neurons of the current layer equals the number of output features for the linear layer. The input layer is, however, slightly different in that the number of input features is equal to the total number of elements of each data sample. For MNIST, this is 28 times 28 features because that corresponds to the shape of the images. Don't forget also to flatten your images prior to passing them through the linear layer. This isn't convolutions. A regression just wants to treat each data point in your image independently and consider the whole thing as one long feature vector. So in summary, looking through the framework one more time in a bit more detail, you first need to define your network architecture, overloading from the nn.module, and then defining and parameterizing the layers in the constructor and piecing them together in the forward function. This is the most complicated bit, but you will get lots of practice in it over coming weeks. Once you've done that, then you need to create an instance of your network and choose and create a loss function and optimizer. Then you're in a position to train. In the simple example I gave in this lecture, I passed all of the input data at every iteration, but this won't be possible for large image datasets, which is why you need the custom datasets and data loader discussed in the last lecture. Then, in the body of the training loop, you first clear the gradients, then you forward propagate in one line, something like this. Then you estimate the loss for the prediction, which is returned, and then back propagate, calling backwards on the loss tensor. And finally, you take a step in the direction of decreasing gradient using the optimizer. Please now go through this final Pete's quiz for this week to check your understanding.